Hey, welcome back. Just when you thought you were done with the standard deviation, wait, there's more.
Oh, yeah!
So, a few more concepts that I want to talk about before we move on to bigger, better things. All right? So, what I want to talk about here is what are called conceptual versus computational formulas. Now, what we've just gotten done doing is conceptual. I took you through the concept of working out a formula for the standard deviation. I tried to make the slow, methodical point that the standard deviation is really nothing more than another kind of average. It's sort of the average amount that the scores differ from their average. Okay, so that was the concept that I hope was understandable. So the formula that we worked our way into is called a conceptual formula. Now, there's computational formulas out there, and they come from the days of old, which are unfortunately not quite old enough yet, when people were inclined to do calculations by hand, all right? So when you have to do things by hand, it makes sense to reduce the number of steps that you have in your calculations. And so the math nerds, the stats wizards, over the years had come up with what are called computational formulas to substitute for the conceptual ones. Now, the computational formulas, as you're about to see, are scarier and uglier looking, but easier to use in the long run when you're doing things by hand. Now, these days, we turn far more readily to computers to do these chores for us, but we stats professors haven't yet quite thrown away our calculators and made you do so either. So I am somewhere in a middle ground here, all right? I see some value in rolling up your sleeves and learning how to do this stuff by hand to help you understand the concept better. I agree that there is something to that old-time wisdom of doing it by hand. But at the same time, I recognize we don't do things by hand anymore. We just don't. But I fear that we won't understand the concepts very well if we jump right to the computer, right to Excel or right to SPSS to do our statistics for us. It's important that we understand what these machines, what these magical machines are doing in order for us to understand conceptually what statistics are about and what they're doing for us. So I'm still having you do some stuff by hand, but I compromise by not having you do these nonsensical computational formulas. So, yikes, that's scary. Don't be too scared by this, okay? On the side over here, I have what are called the conceptual. This is the conceptual formula that we worked our way into, okay? The population standard deviation, or the standard deviation for a sample, is equal to this little formula. You add up the squared deviations, divide by the number of them, hence the average part of it, and then we took the square root of it, okay? So that was the concept that I walked you through, and I hope you now can get. All right? Now don't panic if you look down below it. I just hash it out to say, look, this is for a population, and it's a population set of data. We'll call it sigma, and expanding out that little x, the deviation, I just kind of remind you where you got it. You take each score, subtract its population mean from it, square it, and do the rest, okay? When it's a sample, we'll call it S, and we'll use x bar for the mean instead of mu for the mean, okay? So anyway, these are just the two identical formulas which are substituting for this even more brief conceptual formula, okay? Now over on the other side of the fence are what are called there's a couple of versions for what are called computational formulas. Now, depending on which stat book you open up and look in, or which professor you take stats with, they're likely to use one or the other of these. Your textbook uses this top one, but some textbooks use the bottom one. Now, they're identical algebraically, but they appear to be different formulas, okay? So they're mathematically identical, and they're identical to the formula over here, the conceptual formula. Okay, so do you see what I mean by computational formulas? Kind of are a little bit more frightening to look at, But if you notice, there's no little x's in here. So all you have to deal with are the raw scores, okay? So there's no need to go calculate the little x's, the deviation score. So essentially think of it this way. If you were doing things by hand with a calculator or adding machine in the really old days, these formulas would save you probably about one keystroke per data point, okay? Now, that would add up, over a lot of data. If you're crunching, putting it into a calculator, one less keystroke per number would be a nice, savings in time. So, all right, now notice that the concept, I feel, kind of gets lost in here, okay? Back over here on the conceptual side, I hope by now you're really agreeing with me and understanding what I was trying to impart, that the standard deviation is nothing more than sort of an average. You add up something and divide by the number of it. We did some squaring and then some unsquaring, but it's essentially another kind of average, okay? I think those concepts are a little harder to see if we went jumping straight over to a computational formula. Okay, yes, we divide by n in the bottom over here. That looks familiar, and we're adding some things, but all this other stuff in the numerator, it's really hard for you to understand. I can't see the concept. So if you can't see the concept, I'll totally understand, because I can't see the concept of a standard deviation when I look at the computational formula. But again, they're quicker and easier to use if you're doing things with calculators. Now, so your textbook and lots of textbooks and lots of stats professors start by teaching you the conceptual formulas. Then as soon as you're good and ready with those, they say, okay, we're not going to use those. Here's a bunch of ugly computational formulas, and these are the ones that we're really going to use. And then they would waste a lot of time getting you to, familiar with how to use this formula. And then they would ultimately tell you, but you know what, we never do stuff by hand anyway, so now let's learn how to do it with Excel or SPSS or some other stat program. Excuse me. So I'm going to skip this whole step on the computational side. Yes, you'll see them in your textbook, and you'll see them in most textbooks, but and you're welcome to use them if you want to. Go nuts, okay? So I will never require that you compute a standard deviation using a conceptual formula. So there they are. They exist, and maybe you'll agree with me that, hey, let's not bother wasting our time learning how to do yet another way of doing things by hand. In class and in homework and on tests and things, I'm not going to have you do big, huge piles of numbers. So the cost savings of, that we get over here in the computational side is really trivial. I'd rather you know the concept, and I encourage you to use the conceptual formula. Okay. So that's not just for the standard deviation, but for everything else that we're going to be doing. We aren't going to concern ourselves in class with computational formulas, all right? So when we have to do things by hand, we'll use small data sets and conceptual formulas. When we have bigger things to do, we'll turn to the programs, okay? All right, that was one of the concepts that I want to cover in this video. The other is I want to take things up a notch here. So now that you know what standard deviations are, now that you know how to compute them, now that you know the different symbols that we use for samples and populations, and now that you know that there are conceptual and computational formulas to do this kind of nonsense, it's time to yuck things up a little bit for you. So here comes the big, deep thought for this presentation. Okay, it turns out that we have a little problem when we're calculating standard deviations, especially with small data sets, small samples. If we do research with a small sample, it turns out that when we're using that sample to estimate what a population would be like, what the population standard deviation would be, for example, these conceptual formulas that we learned tend to be biased, all right? Now, let me explain, all right? Now, first of all, you might be wondering, what do I mean by a small sample? And I don't have a firm number to give you for a small sample. If you push me, I'll resort to saying 10. If you've got less than 10, you have a small data set, okay? But I could also, sometimes 20 or even 30 is still a small data set. And it depends on the need, okay? So there is no single number I can give you, but rules of thumb are like 10 to 30, you're in small sample territory. Look at it this way: if I'm doing a population poll, voting poll, to determine voters' preferences for candidates or something, presidential candidates during an election year, for example, are you going to trust a poll that has polled 20 or 30 U.S. citizens to find out who's going to win the national presidential election? Okay, that would be a dinky small sample. All right. Well, how about when I do research in my research methods course next semester? Well, yeah, having 20, 30 observations in each one of your experimental conditions, say your control group, your experimental group, for example, kind of small. Okay. So anyway, the other thing that's confusing here is I said that these small samples, the standard deviation that we calculate from them tends to be biased. What do I mean by that? They tend to underestimate the real population standard deviation. So it turns out that when we calculate a standard deviation for a sample, a small sample, the number that we get likewise tends to be too small. It tends to underestimate what the true population spread is. Okay? Now let me give you an example of this, and I think you'll hopefully immediately agree and understand why it tends to be too small. Okay, picture yourself in any one of your classes. Okay, you got 20, 30 people in a typical class, right? Look around the room. Okay, everybody varies on all kinds of details. Okay, intelligence. Some people are smarter, people are less smart. Okay, people vary across the dimension on intelligence. Okay, height, weight. Okay, how people smell. Okay, now if you look around a typical classroom, you probably don't have the smartest human being in the classroom. You don't likely have the dumbest human being in your classroom. You don't have the tallest people in your class. You don't have the absolute shortest person or people in your class. You haven't got the worst smelling person. You might think you do, but you don't have the worst smelling person possible in your room, and you don't have the sweetest, nicest, most pleasant smelling person in your room. Okay, so
What's that smell? What smell? Ooh. You stink. What do you mean I stink?
Small samples tend not to have as much variability. Okay, they're samples of the big population. A class is a random sample of students, if you will. Okay, so you don't likely have all those extremes. You don't have the smelliest and the sweetest smelling person in the room. Okay, so if I'm going to use that sample to estimate what the population standard deviation of smelliness is, it's probably going to be restricted because the sample is restricted. You dig? Does that make sense? Okay, so since our samples are restricted, the standard deviation that we calculate from it, if we're going to use it to estimate the bigger population, tends to be too small. Now I want to make something very clear. If you do the math right, the standard deviation for that sample is going to be correct. I'm not saying the standard deviation is too small for your sample. I'm saying that your sample is too small to estimate the population. So the standard deviation that you got correctly for that group of numbers is probably not as big as the standard deviation is for the real population that they came from. Okay? Okay, so I hope that makes sense. So we worry about small samples being crappy in lots of ways, and one way that they tend to be crappy is the standard deviations that we calculate from them are crappy estimates of the population standard deviation. So we need a fix. Okay, we need a solution to this. Well, the stats nerds have given us one. Okay, so it's not terribly complicated. Yours is not to ask why this solution works, unless you are, if you're really curious about that kind of detail. Maybe statistics is your field. Okay, maybe you're real interested in that. Most of us are consumers of statistics. I personally don't really care why this fix works. I'm happy that it does work. Okay, I like using computers. I know a thing or two about how they work, but I don't need to know every detail. I like driving a car. I know roughly how they work, but I don't need to know every single detail. I like using my brain. I know roughly how it works, but I don't know every single detail. Okay, so I don't understand why this fix works. I just enjoy that it does. So the solution that we're going to do is twofold. One, we're gonna change our symbol for the standard deviation when we're using it to estimate a population. So again, we're starting with S, which is a sample standard deviation, and we put a little doohickey on top of it. Okay, we call it very creatively S hat. Okay, S with a little hat on top of it. That tells the reader that, hey, I'm doing a little fix to my standard deviation so that I can use it to estimate the bigger population. Okay, so here's my conceptual formula, and here's the fix down here. Okay, so instead of dividing by just n, we divide by n minus 1. So 1 less than the sample size. Okay, now why minus 1? Why not minus 2? Why not some other, why not 0.5? Why 1? Again, if you need to know why, maybe stats is for you. Okay, I don't care why. Okay, they say fix it by doing n minus 1, and I go, okay, I'll do that. All right, now that's going to be our solution when we have a small sample and we want to use it to estimate a bigger population. Now keep in mind that if you want to know what the standard deviation is for that little small group of people, don't correct it. Just do S. Just use the S formula. Okay? But generally, you and I are in psychology doing research to understand not the samples that we're researching, but we're using that sample as a tool to understand some bigger group that we don't have access to. And so we will very frequently be using this. Microsoft Excel and SPSS assume that you want to use this corrected n-1 formula. And you should know that when you ask SPSS or Microsoft Excel to compute a standard deviation, in the background magic of the program, it's using this n-1 version, and sometimes it doesn't tell you. So you know when you get a standard deviation, do know that by default those two programs have calculated the n-1 version. If you need to know what the number is for the sample, Microsoft Excel gives you the option. You can dig out that formula and do it manually. Okay. Truth be told, I don't know how to make SPSS do it. There's probably a way to code it when you program SPSS with code, but pull-down menus don't give you the option. Okay, so why do they do that? Why do they assume that you want S hat? Well, they just figure you're going to be like most researchers, and you need that solution. Okay, now if you have a big sample, this all doesn't matter anyway. Okay. Let me say that again. If you have a big sample, this correction winds up being absolutely trivial. Okay, so when your sample's already big enough, there's no difference between S and S hat. Think of it this way. What's the difference between a room that has 10,000 people in it? Take away 1. Now there's only 9,999 people. Can you tell the difference between 999,000 and 9,999 and 10,000 people? No. You probably can't tell the difference between 100 and 99. All right? So when you have a big sample, the difference between S and S hat becomes nonsensical. Who cares? So SPSS says, you know what? If your data is big enough, then it doesn't matter. We're just going to give you S hat. Okay? So where does that leave us? That leaves us with this giant possibility. Okay? So, yep, you panicked. You almost soiled your shorts here looking at this page here. All right? So break it down here, all right? So on the left side we have conceptual formulas, and on the right we have computational formulas. And here's a quick little preview. We're not going to do computational formulas, so let's not worry about that whole side of the situation here. All right? So, and I'm just breaking it out. So for samples, we have this conceptual formula, or this just slightly more elaborate version of it where I tell you where x came from, little x came from. Okay, a score minus its mean. If it's a population, for populations, we use sigma, all right? And the formula is going to require us to subtract the population mean, mu, okay? And then lastly, when we're going to use the sample to estimate a population, we're going to use the S hat version and divide by n-1. Okay? So that's a little quick summary of the formulas that we're using. All right? And again, no need to worry about that whole half of the side. Okay. So that's just about everything you need to know about the standard deviation. So you now kind of have three versions of it, two of which are kind of identical, and they only differ whether you're referring to a sample or a population, and then the S hat version when you're using a sample to estimate the bigger missing population. And that's that. We're going to use the standard deviation the rest of the semester, so stock that away in your utility belt. Try out a few practice problems. Go back and review that other presentation I made and do some of the practice problems that are in your book. And I'll probably be assigning you some as well. Okay? So that's it for the standard deviation and measures of variability.
Ah, you're crazy.
Am I? Or am I so sane that you just blew your mind?
It's impossible.
Is it? Or is it so possible that your head is spinning like a top?
It can't be.
Can it? Or is your entire world just crashing down all around you?
All right, that's enough.
Yeah!